Okay, this is a recent picture of Burt Rutan. As you can see from some of the other pictures, he's aged a little bit. Those sideburns are his tradition, his trademark. He's never changed them all the years that I've known of him or about him or known him personally. I met him a couple times. But that's his trademark. So we were talking before about an aircraft that would haul rockets up to altitude, release them, and then they would continue on into orbit or to the moon or to Mars, whatever. And a few years ago, he built what by wingspan alone is the world's largest aircraft. It is so big that the wings are much, much longer than a football field. That's just one of the fuselages. One of them. There are 2 fuselages and 6 jet engines from a 747 to power it. I don't believe it has flown yet. At least I can't confirm that it's flown. But at least we can take a look at some of the things that... Yes. What? They made the hangar what? Say it again? They built the hangar big enough to hold the airplane, but they knew how big the wingspan was going to be. It is nothing more than a giant aircraft, so big that it dwarfs almost anything flying today. So what happens is that the rocket, I'd appreciate it if people just kept their mouth shut while I'm talking. Because if you can't keep your mouth shut, then my suggestion is you sit in the back of the room facing the wall like you used to do in grammar school. Kind of a harsh way to do it, but the only way I can think of to keep your mouth shut. Underneath the center of the wing here is where the rocket hangs, and you'll see another video coming up that will show where the rocket hangs onto. Airport. Since this is part of the lecture today, I assume you're all taking notes.
It's huge.
Yeah, I think we just saw this one, but let's take a look here and see.
It's huge, and it is finally, and I do mean finally, after years of talk, getting to the point where it may have its first test run.
Who is behind this plane?
So this is Paul Allen's project.
Right.
He's, very early at Microsoft and a billionaire with a love of rockets. Not the first, mind you. There are a lot of billionaires, it turns out, with love of rockets.
What total cost?
Total cost, goodness, 385.
No, but what do you think it's going to be? I mean, is that?
Impossible to guess, and so far over what we have thought.
And so the thing I can't figure out about this plane is what it's supposed to do that's so much better than every other plane.
Well, better is sort of one of those qualifiers. I can't tell you that. But what this plane is supposed to do to begin is to take rockets up into
Right.
the air and launch them, right? But secondarily, the thing that they have touted for years and that you can finally read about in Wired's story this month is this secret project called Black Ice that is eventually going to be a manned spacecraft, a shuttle, if you were.
So where?
Shuttle like we already had and discontinued?
Oh, and discontinued. Did you ride on the shuttle?
You mean one that consumers can go up in?
His bet is that, well, he hasn't said who will be the passengers for it, and he is much more reticent than, say, Richard Branson to say that this is going to be a consumer product. But his guess is people.
Right. So speak to this, though. So there's now this race to space or race to the air, whatever, between you now Elon Musk, who's being a little grounded.
I don't like that one.
It became apparent that the airplane, there was something wrong. If we look at the fuel flow data to the engines, it looked okay. It looked on speed. Right at any given time we could see that he's burning 8 gallons an hour, for example. That was good data, and it was favorable. But if we look at what was supposed to be our way of determining how much fuel there was in the engine, or in the airplane, and that was, as we pumped it into this header tank, we measured it going in. And then we knew how much was in the header tank. So by measuring how much we took out of each tank, we knew how much was in each tank, and therefore knew how heavy the airplane was, how much fuel it had. Those numbers didn't agree. Those numbers said, we've got a problem, we're using too much fuel.
It was alarming information. It threatened the success of the flight. And it also caused some hard feelings between Bert and Dick Rutan.
Dick was flying higher than he should have. He was flying, he was going around weather. He even turned back once. He circled once, and he had to richen the engines, and he ran the front engine much longer than we thought was going to be needed. And we were thinking that he was flying the airplane sloppy and using too much fuel.
That kind of opinion wasn't calculated to keep Dick calm and contented. With the crew becoming more and more fatigued, discretion was essential.
There were times during the flight in which it was deemed by the doctor and by everyone else, talk to them. They've got to be talked to. They're bored to where they need someone to talk to. They need emotional support. They need encouragement. Get on the radio. Everybody get in there and talk to them. There were other times during the flight when the word was, they're extremely irritable. Don't talk to them.
I mean, one of the most constructive things we did was keep Bert off the radio, because he would immediately become very technical and very logical or whatever, and it just wasn't a time for that. And he and Dick would start fighting, so after a while we took him in the office and kind of pounded on him and stay away, go home, do whatever, but stay off the radio.
Approaching the Philippines, a major problem occurred. The autopilot, essential to the Voyager's flyability, failed. Gina had to work her way under the instrument panel to wire in the backup system, while Dick continued to fly the airplane. That was one problem fixed, but the fuel consumption question remained.
We studied the data of the fuel flow indication, and we studied the fuel system. And what was interesting was simultaneously on board the airplane and on the ground, we both figured out what was possibly happening there. And then Dick saw the bubbles running backwards very slowly in the fuel line, and sure enough, we were sending fuel back to the fuel tanks that was not being measured. Now, wonderful news. We've got more fuel than we think we do. Bad news. Nobody knew how much.
But that was the least of Dick and Gina's worries. They had reached one of the most critical stages of the journey. They were 5 days into the flight. The front engine was shut down and Gina was at the controls. They were approaching Africa. Since the beginning of the flight, their weather expert Len Snellman had been saying that Africa's weather would be impassable. And at the point the Voyager was crossing, there was political turmoil on the ground. There was a real possibility of a SAM missile or a stray bullet bringing the journey to an end. And then the climb began. For most of the journey, Voyager had been flying at about 10,000 feet. Now they were forced to double that altitude to avoid the high mountains in front of them. Back in Mojave, the weather people watched great storms forming in the Rift Valley and passed on directions for avoiding them. But Dick took his own direct route across the north side of Lake Victoria, trying to avoid the storm clouds. They climbed to 20,000 feet, and at one point Gina passed out from lack of oxygen. Dick thought she was dead. He began to have hallucinations of his own. To gain altitude, they'd had to restart the front engine. With 2 engines running, the noise was deafening. The electronic noise cancellation system had failed early in the flight, and the only things that saved them from permanent hearing loss were the form-fitting headphones that blocked out the worst of the sound waves. Africa was a nightmare, but once past the mountains, they began to descend, and as they crossed the coastline and headed out into the Atlantic, the hard-nosed Dick Rutan found himself weeping. But after 6 days of constant noise, lack of sleep, equipment failure, and confinement in a space the size of a phone booth, they were still only 2/3 of the way around the world. And then the weather struck. They were in the middle of a thunderstorm. It took hold of the Voyager and began to roll it over. There was nothing Dick or Gina could do. Then suddenly, they were through the storm, and Dick had to use all his fighter pilot skill to bring the Voyager back to straight and level flight. There'd been some bad moments for Dick during the flight. At high altitude over Africa, he'd hallucinated that the instrument panel was bulging, about to explode outwards. Now, off the coast of South America, extreme fatigue drove him to his lowest point. He could no longer recognize the instruments. Gina took over. After 3 hours sleep, Dick was okay, and he was back in the seat when the next disaster struck. Flying up the Mexican coast, a fuel pump failed.
When the back engine quit, the last night out, and the airplane started to go down, we stopped being able to communicate with them. And I remember I was talking on a microphone, and they disappeared, and I thought, well, that's it, I'm not going to see them again. And I knew all he had to do was pull the nose up, and fuel would flow back to the engine, and he knew he had to keep the nose down to keep the speed, the wind blowing the propeller around. So it was a real conflict, and we argued a little bit about that. And then when the front engine started, he immediately pulled the nose up, and the back engine started, and then they started coming back.
Now they needed just 28 gallons of fuel to fly home. But to get it, they had to replumb the fuel pumps. Gina got the tools together and cleared the space for Dick to make the switch. He was worried that there might be some stray fuel lying around and a spark could ignite it. There was a maze of plastic tubing, and Gina held a flashlight while Dick moved a line from one pump to another. But when they finished, it didn't work. Then they remembered another valve. They changed it, and fuel started to flow again.
finally got down to where we had enough fuel in the header tank to know that we could make it back to Edwards. Just enough. We were sucking little bits of fuel out of where we could find them and bringing the level up to that magic 13 gallons that we needed in the header tank to get home. And as soon as that happened, enormous relief, the airplane was going to make it.
Bert Rutan and Mike Melville flew out in the dark morning to meet the Voyager and welcome it home.
We made a turn, and we looked over there, and we saw a flashing beacon. And we said, "We think that's you. Turn off your beacon light." And they did, and it went off. So now turn it back on. And for some reason, we just all broke down in tears.
It was really something. It's really something.
Oh, Showman Dick showed up at the last time after all this of being exhausted and what they've been through. Here comes Showman Dick with the velvet arm. He has to do a low pass, and then he has to do another one, and we're going, come on, Dick, land it, just get on.
I think the program could not have been successful without two people like Dick and Gina. In spite of the fact that they didn't get along, in their love affair collapsed. Professionally, they did very well. They really were a good support team for each other. I'd like to have dreams that maybe I could have done a flight like that, but I believe I'm as good a pilot, but I don't have the determination. And I think that, I doubt that Dick even has the full determination. I think it was Gina that had the absolutely unstoppable determination that she was going to do this thing, and she didn't care if she died trying. That was what she was going to do. And I really believe that's why they succeeded.
The Voyager and its crew had made it around the world unrefueled. No one had even come close before. Dick and Gina went their separate ways, and the Voyager was presented to the National Air and Space Museum.
Okay, so now the next challenge is we're going to watch a weather tutorial. It's about 17 minutes long. And because the narrator moves rather quickly, you're probably going to be only able to make the kind of notes that you think are important, and you might only be able to abbreviate the information that you're going to take down. So part of the quiz tomorrow is probably going to touch on a question like, what did you think were some of the more important elements that you watched and made note of during the video presentation? It's about weather. It's about how weather develops. It's about the troposphere and the stratosphere and the tropopause, and it talks about various things regarding the initial development of weather. But I'm more interested not necessarily in how you're going to come up with all this information. You're not going to be able to do it. The video moves too rapidly, and the lady who narrates it talks too quickly. But what I want to see from you, and this is going to be a personal decision on your part, so any questions that I ask that have to do with something regarding the video are going to be more questions involved with, what did you think? What information did you get from the video that you thought was more important than other pieces of information? Again, because you're only going to be able to record it quickly, or you're going to try to remember it and then record it, whatever. Okay? So let's go ahead and watch the video. I think it's about 17 minutes. That'll put us about 37 minutes of 2:37. And then we'll have a talk about the video itself and about weather in general. And I might even want to review with you one of the videos that we saw when I showed videos that had to do with gliders and soaring. But we're not going to look at that entire video or PowerPoint presentation. We're only going to look at parts of it that pertain to weather. So let's go ahead and we will look at, how about the sound? Was the sound level too loud?
Tutorial 11, Weather Theory. This lesson will cover weather theory. Understanding the theories behind weather helps a pilot make sound weather decisions based on the reports and forecasts obtained from a flight service station weather specialist and other aviation weather services.
Is that too loud?
In any given volume of air, nitrogen accounts for 78% of the gases that comprise the atmosphere,
You remember
while
that, don't you?
oxygen makes up 21%. Argon, carbon dioxide, and traces of other gases make up the remaining 1%. This cubic foot also contains some water vapor, varying from 0 to about 5% by volume. This small amount of water vapor is responsible for major changes in the weather. The atmosphere is made up of 4 distinct layers that extend up to 350 miles from the Earth's surface. The first layer is the troposphere, which extends from the surface to 20,000 feet over the poles and 48,000 feet over the equator regions. Most weather happens in this region, and the temperature drops by 2 degrees Celsius for every 1,000 feet of altitude gain. The pressure also drops by an inch for every 1,000 feet of altitude gained. Above the troposphere and before the stratosphere, there is a region called the tropopause. This region traps moisture in the troposphere and the associated weather. Above the tropopause are 3 more atmospheric levels. The first is the stratosphere, which extends from the tropopause to a height of about 160,000 feet. Little weather exists in this layer, and the air remains stable, although certain types of clouds occasionally extend in it. Above the stratosphere are the mesosphere and thermosphere, which have little influence over weather. The atmosphere is in constant motion. Certain factors combine to set the atmosphere in motion, but a major factor is the uneven heating of the Earth's surface. Earth is warmed by energy radiating from the sun. The process causes a circular motion that results when warm air rises and is replaced by cooler air. Because the Earth has a curved surface that rotates on a tilted axis while orbiting the sun, the equatorial regions of the Earth receive a greater amount of heat from the sun than the polar regions. Solar heating causes higher temperatures in the equatorial areas, which causes the air to be less dense and rise. As the warm air flows toward the poles, it cools, becoming denser, and sinks back toward the surface. The unequal heating of the Earth's surface not only modifies air density and creates circulation patterns, it also causes changes in air pressure, or the force exerted by the weight of air molecules. Although air molecules are invisible, they still have weight and take up space. Imagine a sealed column of air that has a footprint of 1 square inch and is 350 miles high. It would take 14.7 pounds of effort to lift that column. This represents the air's weight. If the column is shortened, the pressure exerted at the bottom and its weight would be less. The weight of the shortened column of air at 18,000 feet is approximately 7.4 pounds, almost 50% that at sea level. The actual pressure at a given place and time differs with altitude, temperature, and density of the air. These conditions also affect aircraft performance, especially with regard to takeoff, rate of climb, and landings. The force created by the rotation of the Earth is known as the Coriolis force. This force is not perceptible to humans as they walk around, because humans move slowly and travel relatively short distances compared to the size and rotation rate of the Earth. However, the Coriolis force significantly affects bodies that move over great distances, such as an air mass or body of water. The Coriolis force deflects air to the right in the northern hemisphere, causing it to follow a curved path instead of a straight line. The amount of deflection differs depending on the latitude. It is greatest at the poles and diminishes to 0 at the equator. The magnitude of Coriolis force also differs with the speed of the moving body. The greater the speed, the greater the deviation. As shown above, the speed of the Earth's rotation causes the general flow to break up into 3 distinct cells in each hemisphere. This circulation pattern results in the prevailing westerly winds in the conterminous United States. Circulation patterns are further complicated by seasonal changes, differences between the surfaces of continents and oceans, and other factors such as frictional forces caused by the topography of the Earth's surface, which modify the movement of the air in the atmosphere. Thus, the wind direction at the surface varies somewhat from the wind direction just a few thousand feet above the Earth. Atmospheric pressure is typically measured in inches of mercury, Hg, by a mercurial barometer shown on the left. The barometer measures the height of a column of mercury inside a glass tube. A section of the mercury is exposed to the pressure of the atmosphere, which exerts a force on the mercury. An increase in pressure forces the mercury to rise inside the tube. When the pressure drops, the mercury drains out of the tube, decreasing the height of the column. This type of barometer is typically used in a laboratory or weather observation station, is not easily transported, and difficult to read. An aneroid barometer, shown on the right, is an alternative to a mercurial barometer. It is easier to read and transport. The aneroid barometer contains a closed vessel called an aneroid cell that contracts or expands with changes in pressure. The pressure sensing part of an aircraft altimeter is essentially an aneroid barometer. It is important to note that due to the linkage mechanism of an aneroid barometer, it is not as accurate as a mercurial barometer. To provide a common reference, the International Standard Atmosphere, ISA, has been established. These standard conditions are the basis for certain flight instruments and most aircraft performance data. Standard sea level pressure is defined as 29.92 inches of mercury and a standard temperature of 59 degrees Fahrenheit, 15 degrees Celsius. Atmospheric pressure is also reported in millibars, with 1 inch of mercury equal to approximately 34 millibars. Standard sea level pressure is 1013.2 millibars. Typical millibar pressure readings range from 950 to 1040 millibars. Since weather stations are located around the globe, all local barometric pressure readings are converted to a sea level pressure to provide a standard for records and reports. To achieve this, each station converts its barometric pressure by adding approximately 1 inch of mercury for every 1,000 feet of elevation. For example, as shown above, a station at 5,000 feet above sea level with a reading of 24.92 inches of mercury reports a sea level pressure reading of 2992 inches of mercury. Using common sea level pressure readings helps ensure aircraft altimeters are set correctly, based on the current pressure readings. As pressure decreases, the air becomes less dense, or thinner. This is the equivalent of being at a higher altitude and is referred to as density altitude, dA. As pressure decreases, dA increases and has a pronounced effect on aircraft performance. Altitude affects every aspect of flight, from aircraft performance to human performance. At higher altitudes, with a decreased atmospheric pressure, takeoff and landing distances are increased, as are climb rates. When an aircraft takes off, lift must be developed by the flow of air around the wings. If the air is thin, more speed is required to obtain enough lift for takeoff. Therefore, the ground run is longer. An aircraft that requires 745 feet of ground run at sea level requires more than double that at a pressure altitude of 8,000 feet, as shown in the figure above. At sea level, atmospheric pressure is great enough to support normal growth activity and life. by 18,000 feet, the partial pressure of oxygen is reduced and adversely affects the normal activities and functions of the human body. The reactions of the average person become impaired at an altitude of about 10,000 feet. But for some people, impairment can occur at an altitude as low as 5,000 feet. The physiological reactions to hypoxia or oxygen deprivation are insidious and affect people in different ways. These symptoms range from mild disorientation to total incapacitation, depending on body tolerance and altitude. Supplemental oxygen or cabin pressurization systems help pilots fly at higher altitudes and overcome the effects of oxygen deprivation. Air flows from areas of high pressure into areas of low pressure because air always seeks out lower pressure. In the northern hemisphere, the flow of air from areas of high to low pressure is deflected to the right and produces a clockwise circulation around an area of high pressure. The opposite is true of low pressure areas. The air flows toward a low and is deflected to create a counterclockwise circulation. High pressure systems are generally areas of dry, stable, descending air. Good weather is typically associated with high pressure systems for this reason. Conversely, air flows into a low pressure area to replace rising air. This air tends to be unstable and usually brings increasing cloudiness and precipitation. Thus, bad weather is commonly associated with areas of low pressure. A good understanding of high and low pressure wind patterns can be of great help when planning a flight, because a pilot can take advantage of beneficial tailwinds shown above. When planning a flight from west to east, favorable winds would be encountered along the northern side of a high pressure system, or the southern side of a low pressure system. On the return flight, the most favorable winds would be along the southern side of the same high pressure system or the northern side of a low pressure system. While the theory of circulation and wind patterns is accurate for large-scale atmospheric circulation, it does not take into account changes to the circulation on a local scale. Local conditions, geological features, and other anomalies can change the wind direction and speed close to the Earth's surface. Different surfaces radiate heat in varying amounts. Plowed ground, rocks, sand, and barren land give off a large amount of heat. Water, trees, and other areas of vegetation tend to absorb and retain heat. The resulting uneven heating of the air creates small areas of local circulation called convective currents. Convective currents cause the bumpy, turbulent air sometimes experienced when flying at lower altitudes during warmer weather. On a low-altitude flight over varying surfaces, updrafts are likely to occur over pavement or barren places, and downdrafts often occur over water or expansive areas of vegetation, like a group of trees. Typically, these turbulent conditions can be avoided by flying at higher altitudes and even above cumulus cloud layers, as shown by the image above. Convective currents are particularly noticeable in areas with a landmass directly adjacent to a large body of water, such as an ocean, large lake, or other appreciable area of water. As shown by the top images, during the day, land heats faster than water, so the air over the land becomes warmer and less dense. It rises and is replaced by cooler, denser air flowing in from over the water. This causes an onshore wind, called a sea breeze. Conversely, at night, land cools faster than water, as does the corresponding air. As shown by the bottom image, the warmer air over the water rises and is replaced by the cooler, denser air from the land, creating an offshore wind called a land breeze. Convective currents can occur anywhere there is uneven heating of the Earth's surface. As shown above, convective currents close to the ground can affect a pilot's ability to control the aircraft. For example, on final approach, the rising air from terrain devoid of vegetation sometimes produces a ballooning effect that can cause a pilot to overshoot the intended landing spot. On the other hand, an approach over a large body of water or an area of thick vegetation tends to create a sinking effect that can cause an unwary pilot to land short of the intended landing spot. Obstructions on the ground affect the flow of wind and can be an unseen danger. Ground topography and large buildings can break up the flow of the wind and create wind gusts that change rapidly in direction and speed. These obstructions range from man-made structures like hangars to large natural obstructions such as mountains, bluffs, or canyons. It is especially important to be vigilant when flying in or out of airports that have large buildings or natural obstructions located near the runway. The intensity of the turbulence associated with ground obstructions depends on the size of the obstacle and the primary velocity of the wind. This can affect the takeoff and landing performance of any aircraft and can present a very serious hazard. During the landing phase of flight, an aircraft may drop in due to the turbulent air and be too low to clear obstacles during the approach. This same condition is even more noticeable when flying in mountainous regions. As shown above, while the wind flows smoothly up the windward side of the mountain and the upward currents help to carry an aircraft over the peak of the mountain, the wind on the leeward side does not act in a similar manner. As the air flows down the leeward side of the mountain, the air follows the contour of the terrain and is increasingly turbulent. This tends to push an aircraft into the side of a mountain. The stronger the wind, the greater the downward pressure and turbulence become. Before conducting a flight in or near mountainous terrain, it is helpful for a pilot unfamiliar with the mountainous area to get a checkout with a mountain-qualified flight instructor. Please help us spread the word about pilot training systems.
Okay, we covered a lot of that information on previous lectures, didn't we? Like the proportion of nitrogen and oxygen in the air. That was one of them. Talked about density altitude a little bit. So now what I want to do is I want to take your class pictures. So everybody sit up nice and smile. Smile. All right, well, I'll try this. See if I can get everybody in there. Are you all looking? Pardon?
Why don't we go like in front of the planes right there?
Why what now?
Why don't we go like in front of the planes?
No, I want you in the classroom. Does that make any sense? No? As soon as you guys get your drone pilot license, I'll be happy to take a picture of you near the airplanes.